Hi, my name is Yash, and today I'll be presenting the Physics 2212 Lab 5. And the introduction is that the purpose of this experiment is to use the physics behind things like magnetic flux, EMF, and etc. to observe a falling magnet through a conductive tube of aluminum foil. And several models and concepts are going to come into play here. One, the magnetic field, the magnetic force, magnetic flux, EMF, Ohm's law, Faraday's law, and Lenz's law. And as you can see, these are some of the important equations that go along with this lab. For example, the EMF is the derivative of the flux with respect to time. And the magnetic force, one way is to do I times the cross product of L, the length, and the magnetic field. And we also know that force can be written as Q times V cross B. And then magnetic flux can be given using the integral of the magnetic field times the normal vector to the surface times the area. And then Ohm's law, one way to write it is I equals the change in potential difference all over R. As far as the experiment goes, the system is the falling magnet, and then the surrounding is Earth and the aluminum foil tube. And the procedure we want to use is to make sure you have all the materials, including a meter stick and most likely an app on your phone that measures magnets. So the first thing you want to do is mark the north pole of the magnet using the app, and then determine the mass of the magnet. You'll also want to determine the inner radius and length of the tube and the width of the foil. And drop the magnet through the aluminum foil 5 times and record this. And the reason why we do it 5 times is to get accurate results over several trials. Then you want to calculate the average time it takes between the magnet entering and exiting the tube. So the results that we got, as you can see, the times are kind of all over the place, and the average time was 0.7 seconds. The inner radius was 0.0146 meters. The length of the tube was 0.59 meters. The width of the aluminum foil was 0.003 meters. The total radius was 0.0176 meters, and the max of the magnet was 0.025 kilograms. And then as far as the coding goes, this coding will kind of demonstrate how the value of the magnetic dipole moment mu impacts our results. So we put in the values for L with inner radius that were calculated, and from lab 3, the value of magnetic dipole moment is 3.71. And then we calculate the dipole moment here. We calculate the flux, and then we do the force of gravity, and force of gravity points downwards. That's why it's negative mass times g, and then some other calculations to get like the magnetic field. And then the results that we get from this is that when the value of mu from lab 3, 3.71 is used, it takes about 1.495 seconds for the magnet to exit the tube, which doesn't match the value from the lab. However, if we use 2.245 as the value of mu, it takes about 0.7 seconds for the magnet to exit the tube, which matches the value we got from the lab. As far as the discussion goes, we could have gotten errors from like the meter stick, or the fact that our hands might have contributed to the magnet app not being super accurate. And then there's also friction between the tube and the magnet, which could have influenced the results. So to answer the question, what if the resistivity of the conductor were reduced as close as possible to zero? How would it affect the falling magnet? So resistivity we know is similar to resistance, so we would have zero resistance, and then as a result we would have a large current due to Ohm's law, and therefore a large magnetic force. And because of this, the magnet would fall with a lower velocity. To answer the question, what if holes or slots were cut in the tube, and how would it affect the ring currents? The rings would cause the induced current to weaken, and the magnetic force would therefore decrease, and the magnet would fall with a higher velocity this time. So, conclusions are that magnets are very powerful, and many different people have contributed to the theory of magnets, including Faraday and Lenz, and they have laws named after them. And in general, magnets are used all around us.